seminar. It's the second part of the presentation by Maley Bannerджи from Institute of Kanpur, and today's talk is structural sensitivity of spatial temporal pattern formation. Please, Maley, you can begin your presentation.
Okay, so thank you very much, Vitali, for the introduction and also invitation. So last week I had delivered a talk on structural sensitivity on bifurcation structure, and today I am going to talk about this structural sensitivity on spatiotemporal pattern formation. So first, let me give you some preliminary idea about the Turing patterns and others, and different types of patterns as I understand, and it is available in literature, and then I'll discuss about the structural sensitivity. So this is some sort of ecological example where we can see different type of patchy patterns in natural environment. And in this paper by Luca Ridolfi, that was, and his group, it was published in 2011 in Mathematical Biosciences. They have obtained some model, and its simulation produces the result which are in good agreement with the pattern that we observe in natural environment. And although there is a little bit drawback as per my understanding in their formulation, in order to have this non-smooth boundary of these patches, they have introduced a particular type of noise term. And as far as my understanding goes, for their formulation, it would be very difficult to prove the positivity of the solution. But that is not an emphasis of my today's talk. Rather, what I just wanted to explain, that once this kind of pattern is observed in nature, there is some mathematical model through which we can capture such kind of patterns. But one point I want to mention, in this case, we call this as a spot pattern, and spots are generated due to the presence of the biomass, not due to the absence of the biomass. Then for the second one, here you can see some spots, and here the spots are due to absence of the biomass. So that is why this is called hotspot pattern, because spots is generated due to the high concentration of the population, and here is the spot due to absence of the population. So that is why it is called cold spot pattern. And in between you will find this labyrinthine pattern, and I will explain with the help of Turing instability and Turing bifurcation diagram, in which domain we can have this kind of patterns. Now, this is another example, another 3 examples of ecological pattern. Left one is the wetland pattern, middle one is the ribbon forest, and right hand we have the pattern generated by the interaction between bluefin tuna and yellow whale. And these kind of patterns again can be generated with the help of mathematical modeling, and those mathematical models, once we simulate, we can have these 3 types of patterns. And as I mentioned that okay, there are 3 different types of patterns. So this is again a cold spot, this is hot spot, and this is labyrinthine pattern. And once we have these 3 type of patterns, this is a spot pattern, cold spot. This is also a spot pattern, hot spot. But interesting point is that this pattern is instantaneous. You can understand from the ecology that once whale chase the bluefin tuna, at a particular instant of time, this pattern has been produced. And at the next instant of time, you can see there is a change in the distribution of both the species. And what we need to understand, that if we mention that this pattern captures this particular mechanism, then question arises that whether this pattern is dynamic in nature or stationary in nature. Answer to this question is that the model from which we obtained the pattern, that was stationary pattern. And what I am trying to say, in some of the literature, people have tried to explain this as an example of spot pattern and tried to explain this pattern with the help of Turing instability or Turing pattern. But frankly speaking, it is a dynamic pattern and it keeps on changing with respect to time. So continuous time model, which I am going to consider here, that might not be suitable for this kind of modeling approach. Rather, we need some different type of approach like individual based model or fish schooling model or something like that. But what I just wanted to convey here, that patterns can be broadly classified into two types. One is stationary pattern and another is dynamic pattern. So stationary pattern means after some time, it will arrive at a distribution and that distribution will remain unaltered at all future time. And dynamic patterns are the patterns which keep on changing with respect to time. So this is one classical example. And now one can raise the question, can you ensure that these type of distribution will remain there for all future time? Answer is no, because one can easily understand once we have this distribution within 1 or 2 days, if there is a heavy rainfall, so then distribution of the water body and their area will be changed. And as a result, what we can say that these are stationary over a short time scale, but not over an evolutionary time scale or over a longer time scale. This is also for certain time, it can be considered as a stationary pattern, but it keep on changing. And nowadays, evolutionary approach and long transients, those kind of topics comes into the picture. But background or basic idea is the Turing instability condition, and from where we can have some heterogeneous distribution of the solution, and that can be considered as a moderate result or moderate approximation of the real world phenomena, that is heterogeneous distribution of the species, that we can accept for the time being. Okay, now as I have mentioned in the previous slide, basically we can categorize the pattern into two different types with respect to its variation over time. One is stationary pattern and another is dynamic pattern. And now if we look at different types of patterns depending upon their origin or type of initial condition we use or type of instability present within the model system under consideration, there are different types of patterns. One I have already explained, that is spot and labyrinthine pattern. Apart from these two, we have traveling wave, periodic traveling wave, modulated traveling wave, target pattern, spiral pattern, spatiotemporal chaos, pulse, periodic pulses, and so on. Here, I just want to make one comment that sometimes these kind of terminology like target pattern, spiral pattern, etc., these are somehow related to periodic traveling wave also, or even modulated traveling wave also. Once we move from different dimension of space, because in case of spatiotemporal model, for simplicity, one can consider one-dimensional space, one can consider two-dimensional space. In case of aquatic environment, it is much reasonable to consider a three-dimensional space. But for numerical complexity, or in order to have the result within a limited time through numerical simulation, one can consider some lower version, means one-dimensional space. But what I'm trying to say, sometimes we have observed that periodic traveling wave in one dimension can replicate the type of patterns we observe in two dimension, which are target pattern or spiral pattern. So mostly spiral pattern, that means which keep on whirling around an head with an arm, that can be captured through one-dimensional periodic traveling wave, or what we can say, Suppose we are considering a reaction diffusion equation model, and in one-dimensional space, if we have periodic traveling wave, one can ask the question with same parameter value. Instead of one dimension, if we consider that space 2-dimension, what kind of pattern you expect? As far as my knowledge goes, there is no straightforward answer, but I think Vitali is there and Yuri Tutunov is there. They can help me to understand, or they can correct me if I mention something wrong. But sometimes if I have observed in couple of problems that spiral pattern or target pattern at the initial stage of the settlement, they can correspond to one-dimensional periodic traveling wave. Of course, within this talk, I am not going to discuss about that, but just for young researchers, this is a particular topic. If you are interested, you can explore that. Can we make a one-one correspondence between the patterns once we observe in one-dimensional space and once we observe in two-dimensional space? But if you ask me the question why, whether you have tried or not, or whether it is easy to do it or not, I can say no, it is quite difficult. Sometimes with specific cases, and of course for a very special choice of parameter values, I have seen one-one correspondence. But so far as my literature collection or literature survey goes, I did not find any concrete literature which can make a connection between these two. So this is just an observation. So these are different type of patterns we can find in the model which can produce some spatiotemporal patterns. Then the next question arises, what is the simplest model? Of course, I am considering a two-component model. One variable model means only with respect to u, one can have some pattern. But in this talk, I want to confine myself with two-component system only. So u is one component, v is another component. We can consider u as an activator, v is an inhibitor in case of chemical kinetics, or we can consider resource and consumer, we can consider prey and predator, and so on. And even some other applied areas also, they can interpret different types of variables depending upon the area of application. So what it says, that we have two variables, their growth and distribution, growth with respect to time and distribution with respect to space, is governed by these two variables u and v, and their growth and distribution with respect to time and space, they are described by these two coupled nonlinear, non-homogeneous parabolic equation. This is a Laplacian written in terms of appropriate number of space variables, and d is the ratio of diffusivity of the second component over first component. It is a dimensionless quantity. So for original model without non-dimensionalization, if we consider capital du as the rate of diffusion of u component, capital dv is the rate of diffusion of the v component, then d small d stands for dv by du. And this model is subjected to non-negative initial condition at t equal to 0. And for simplicity, what we can consider no flux boundary condition. So that means there is no inflow or outflow of the biomass to the boundary. So these are very simple setup of the model through which we can capture different type of patterns, as I explained in the previous slide. And F and G, these are the reaction kinetics. So this actually describes how U and V, they grow and interact among themselves at a particular special point, that is x or x comma y in case of 2 dimension, or x comma y comma z in 3 dimension. And this is the reaction part. So if we consider there is no distribution with respect to space, it will reduce to corresponding to coupled nonlinear ordinary differential equation. And if we introduce space, so these two components will come into the picture, and they takes care of the fact that they can move over 2-dimensional space in a random fashion. And also for simplicity here, what we have considered self-diffusion only. So that means growth of U and V, that will be influenced by the rate of dispersal of the same species. So that means growth of U is influenced by rate of diffusion of U only, and rate of growth of V is also influenced by rate of dispersal of V only. There are some other models where we can have combination of these two, that of course I'll mention in my after a couple of slides. And then basic idea is that we are just going to find out the Turing instability condition based upon this type of model. So as I have mentioned, other type of models are known as advection diffusion model, reaction advection diffusion model, as well as intrigo differential equation model, and so many other type of model. They can also produce the patterns. But for simplicity, here I consider this simplest formulation. So now the for Turing instability, what we just make an attempt to obtain the condition. So this is a governing system. We are looking for some homogeneous steady state solution. So if we can find out two solution, u of t comma x equal to u star, which is a constant, v of t comma x is equal to v star, which is another constant, which satisfies these condition. So that means u star and v star are feasible solution of these two coupled equation, or these two rather simultaneous equation, not coupled, simultaneous equations. And one can verify that u t comma x equal to u star and v t comma x equal to v star is a solution of this coupled equation also. Now our target is that we want to find out the analytical conditions such that once this homogeneous steady state had perturbed slightly with temporal perturbation, no spatial perturbation, then this homogeneous steady state will remain stable. But if we introduce small amplitude heterogeneous perturbation around this homogeneous steady state, then there will be instability. And in order to find out such conditions, so these three conditions are given. So first two condition corresponds to stability of this homogeneous steady state under temporal perturbation, and the last condition mentioned in red color, that is condition required for the instability of the homogeneous steady state under small amplitude heterogeneous perturbation. And also I mentioned this condition in red not only for the fact that this is the part of spatial component, or it is the crucial condition for the Turing instability. Rather, I want to emphasize here that if we look at these two conditions, that is fu u star v star plus gv u star v star less than 0, and the last condition, we have to keep in mind d is a positive constant. So if these two conditions are required to be satisfied simultaneously, then we should have fu and gv are of opposite sign. So these somehow explain that certain type of temporal interaction or reaction kinetics supports Turing instability. So just for example, if we consider two component classical Lotka-Volterra computation model, so for any parameter value, we can always prove that for coexistence homogeneous steady state, fu is negative, gv is negative, so their sum is negative. So first condition is satisfied, and as both of them are negative, so once the first component is multiplied by a positive constant, so these sum should not be positive. And that is why that Lotka-Volterra computation model cannot produces any Turing pattern, because these two conditions will not be satisfied simultaneously. And one quick example or quick information, that if we look at the sign of the Jacobian matrix for the corresponding temporal model at the homogeneous steady state, if their sign follows a particular pattern, then only one can make an attempt to find out the Turing instability condition. So that pattern is that either one column should contain both the positive quantities, next column will contain both the negative quantities, or one row consists of positive elements and another row consists of negative elements. If Jacobian matrix, that means sign of the Jacobian matrix, follows this terminology, then we can make an attempt to find out the condition for Turing instability. That means for what magnitude of D all these conditions will be simultaneously satisfied. That will give us the range of unstable wave number through which we can determine what is the requirement for optimal domain size over which we can see a significant number of patches. Those are generated through the Turing instability. But keep in mind that if we talk about Turing instability condition, so most of the time through numerical simulation, once Turing instability condition is satisfied, we used to have some sort of heterogeneous distribution as a resulting pattern. Most of the time, not over the entire parametric domain, but within a majority of the domain, we can find stationary pattern. But we have to keep in mind that Turing instability condition ensures only the instability of the homogeneous steady state under small amplitude heterogeneous perturbation. But this instability condition never assures existence of a stationary pattern or a non-stationary pattern. There are several examples where we can see that although the Turing instability condition is satisfied, but we are unable to find out Turing pattern, stationary Turing pattern. Discussion about that part is a quite lengthy. I'm not going into that part, but just I want to mention that Turing instability condition ensures the instability of homogeneous steady state under small amplitude heterogeneous perturbation, but it is not related with the assurance for existence of stationary pattern. Now, let us come to this particular example. This part, although I have mentioned that spatiotemporal Rosenwig-McArthur model, and then I have mentioned Fussman and Blasius, this reference, biology letters in the first volume in 2005. So this paper, that means Fussman and Blasius paper, they have discussed the structural sensitivity of the temporal Rosenwig-McArthur model. So they have worked on this problem with D1, D2, and D21, all these three quantities equal to 0. So there is no special component. And what they have shown that for this formulation, that means this Rosenwig-McArthur model, instead of a particular functional response, if we choose different parametrization of the functional response, we can see there is a significant change in the temporal behavior of the model. So here our intention is to consider that whether introduction of this diffusion term with different parametrization of Fn can lead to some sort of structural sensitivity on the spatial or spatiotemporal pattern formation or not. Okay. Next question arises. In some of the previous slides, I talked about only D1 and D2, that means diffusion in these two components, self-diffusion. But here I'm talking about some sort of cross diffusion. Why? Because one can verify, it is a standard calculation, that if D21 equal to 0, then Rosenwig-McArthur model with self-diffusion term cannot produces any Turing pattern. Why? Because in case of existence of Turing pattern, as I have mentioned, that Jacobian matrix should follow a particular pattern of signs, but for Rosenwig-McArthur model, without this cross-diffusion term, one can easily calculate or easily verify A22 is exactly equal to 0. So that means one element 0 means the requirement plus plus minus minus, that is violated because one element is exactly equal to 0. So here we have considered this cross diffusion just to ensure that this model with Rosenwig-McArthur reaction kinetics can lead to some sort of Turing patterns. And what is the ecological interpretation of this term? Ecological interpretation of this term can be given like that rate of diffusion of the predator is partially guided by the flux of the prey population. So that means they can try to move depending upon the prey density or prey gradient. So they follow the prey gradient in order to have some successful catch. So this is just an ecological interpretation. Now with this one, as I have mentioned, that there does not exist any Turing pattern if D21 equal to 0. But dynamic patterns exist if we consider D21 equal to 0. There are several articles by several renowned persons who have talked about spatiotemporal chaos, wave of invasion, and other different type of dynamic pattern for this spatiotemporal Rosenow-McPherson model with D21 equal to 0. But we can have stationary pattern as well as dynamic pattern once D21 is not equal to 0. With this, what we are going to consider, in last talk I have discussed only Holling type 2 and Ivy, but today I am going to talk about three different functional response: Holling type 2, Ivy, as well as trigonometric functional responses. So here AH, BH, these are the parameterization for the Holling type 2. AI, BI, they stands for Ivy, and AT and BT, they stands for trigonometric functional responses. And one point I like to mention that the parameter values we have chosen for this study is not according to the parameter values chosen by Fussman and Blasius, because at certain point they have considered a particular value of AH and BH, and the same value they have used for AI, BI and ATBT. Instead of that, what we are going to do here, or what we have done in our work, we have estimated AI, BI as well as AT and BT corresponding to a fixed value of AH and BH, such that these three functional forms remains close to each other over a certain range of values of n. So what is the range of values of n we have considered? We have considered the range of values of n that is from 0 to 4. Next question is that what is the guiding factor such that we can have this 0 to 4? One guiding factor is the magnitude of k, because for the temporal model we can prove at long time n will be always less than equal to k. But we have to keep in mind that limit might not be true for the spatiotemporal model under certain circumstances, but for our analysis or for our study, how much we have performed, mainly around the Turing instability and Turing boundary and within the Turing domain. So within that range, we have checked that corresponding to some choice of the parameters, once we look at the corresponding spatiotemporal distribution, most of the time n remains less than equal to k. We did not prove it, but as we have observed through numerical simulation and several numerical trial that it is not crossing the value n equal to k, and k is considered here as 4. So therefore we have estimated this AI, BI as well as AT and BT such that these functions fhn minus fin, this modulus less than epsilon, their supremum, and this fh and ft, their supremum over 0 to k modulus, that should be less than epsilon, and that assumption with epsilon equal to, if I recall correctly, 0.02, we can have these estimates for AI, BI and ATBT. These are given by these values corresponding to AH equal to 3.051 and BH equal to 2.68. So these two values are the same as they have used in this paper that by Fussman and Blasius. So what we have done with these parameter values, now if we calculate the Hopf bifurcation just for the temporal model, there is an interesting observation and that is called criticality. Criticality means we have calculated the Hopf bifurcation threshold for 3 different functional responses. These are the analytical expression for Hopf bifurcation threshold in terms of K. So K can be, that means Hopf bifurcation threshold for carrying capacity can be obtained explicitly in terms of other parameters involved with the dimensionless version. An interesting point is that whatever may be the choice of other parameter values, the Hopf bifurcation for Holling type 2 functional response and Ivy-Lev functional response, they are always supercritical. But once we have trigonometric functional response, these Hopf bifurcation threshold might be supercritical or subcritical depending upon the magnitude of other parameters. So that is why we can say that if we consider the critical nature of the Hopf bifurcating limit cycle, this might be stable or unstable depending upon which type of functional responses we are considering, although the functional responses remain close to each other over the range of n, that is 0 to 4. If we look at the corresponding bifurcation structure, so first one corresponds to the bifurcation structure of the temporal model with Holling type 2 functional response. This one corresponds to Ivy-Lev functional response, and these two picture corresponds to tan hyperbolic or trigonometric functional responses. So these are two different values of m. So for this picture, as well as this picture, m is fixed at 0.5 with r equal to 1. But for this figure, we have considered m equal to 0.6 just to show or just to answer the question if anybody asks that, okay, is it true that all the time if we consider that is tan hyperbolic functional response, we'll have subcritical or supercritical? Answer is depending upon other parameter values, we can have only supercritical, no subcritical Hopf bifurcation, or another parameter set there is subcritical Hopf bifurcation, but stable limit cycle that is generated through a global bifurcation that is called saddle node bifurcation of limit cycle. So this is some sort of structural sensitivity of the temporal dynamics if we consider 3 different parameterization of the functional responses, although they satisfy the similar properties. That means at n equal to 0, it is 0, then monotone increasing and bounded above. Now the last round of question or most interesting part of this talk, that is how it will affect the spatiotemporal pattern formation and what are the consequences of these different parameterization on the resulting spatiotemporal pattern. So this is the Turing bifurcation diagram for Holling type 2 functional response. So this vertical black line is the supercritical Hopf bifurcation threshold that corresponds to k equal to r. Red curve is the Turing bifurcation threshold. So homogeneous steady state is unstable for parameter values above this curve, and heterogeneous perturbation around the homogeneous steady state is stable if we choose the parameter value below this particular red curve, and homogeneous steady state is stable under temporal perturbation if we consider values of k on the left of this vertical line, and it is unstable on the right of this vertical line. So these stability and instability with respect to only temporal perturbation and spatiotemporal perturbation leads to 4 different regions: R1, R2, R3, R4. So in R1, the homogeneous steady state is stable under both kind of perturbation. In R2, homogeneous steady state is unstable under heterogeneous perturbation. In R3, homogeneous steady state is unstable with respect to both temporal as well as spatiotemporal perturbation. And in R4, homogeneous steady state is unstable only under temporal perturbation. So these are the parameter values. And as we wanted to follow some particular procedure, or in order to have the resulting pattern within a particular reasonable domain size, we have chosen D1, D2 as two parameters, but we have considered D1 equal to 1 and D2 equal to 2, just in order to conformable with the fact that in terms of dimensionless model, D1 should be 1. So if anyone wanted to follow that non-dimensionalization, that 1 in diffusivity for predator in dimensionless version, so that also follows from this assumption. And now, if we choose different combination of K and D21, so D21 is chosen as a bifurcation parameter. So for different combination of K and D21, we observe different kind of patterns, and these are listed here. So this is a labyrinthine pattern that is obtained for K equal to 0.8, D21 equal to 1, 2 for parameter value within R2. Once we consider two different sets of parameter value from R3, one is given by this one, another is given by this one. This corresponds to these two different types of patterns. So this is a mixture of stripe and spot. This is only a spot pattern, and we have checked this simulation by performing the simulation over a very longer time. So there is no change. So that possibility that, okay, this pattern might get changed to this pattern if we run the simulation for a longer time, that is ruled out. And finally, if we choose parameter values from the domain R4, which is unstable only under temporal perturbation, but still it produces some dynamic pattern. One is the spiral, of course, with long, means thick arm, and then for another value of K that is equal to 4.5, we have this interacting spiral chaos. Of course, one can say that this is not your exactly spiral, because we can see some branch or some other things can comes in this particular region. So what we can say that here we have observed spiral at least with 2 rotation, but for this parameter value, we were unable to find out a spiral with at least 1 complete rotation. So this might be some sort of interacting spiral, but if we look at its corresponding temporal evolution of the spatial average, then we can find two completely different scenario corresponding to these two patterns. So once you can see some sort of quasi-stationary distribution, which corresponds to this spiral, and this interacting spiral corresponds to this type of irregular distribution, and practically it is actually chaotic distribution. We verified it with the help of Lyapunov, spatial Lyapunov exponent. But interesting point is that in both the situation, we can see long time coexistence of both the species, but they are far away from the homogeneous steady state. And I must acknowledge Professor Yuri Tutunov. Once I collaborated with him about one paper on prey taxis, he introduced me that this kind of presentation gives us a clear-cut distinction between the temporal dynamics and spatiotemporal dynamics. So this is the attractor, this red dot is the attractor for the temporal model. So if we don't have any spatial perturbation, if we consider the reaction kinetics only, so from wherever we start, trajectory will always converge to this level. So this is the coexistence level of both prey and predator in the absence of diffusion. Once we introduce diffusion into the system, then we can find some oscillatory coexistence, and their population levels are quite different from the temporal counterpart. And what we can observe, that introduction of space actually increases the prey density at their coexistence state, but predator population declines. Wherever, if we change the carrying capacity without changing the cross diffusion coefficient, and change in carrying capacity results in spatiotemporal chaos. But here we can see, in the context of spatiotemporal chaos, both U and V, that means N and P population, they have been increased compared to their temporal counterpart. So this is a understanding of two different type of patterns, and as it is a quasi-periodic structure, we can observe for the temporal evolution of the spatial average. So this is not chaotic, but on the other hand, here we can see this is clearly chaotic attractor, and that is why we call this as a spiral pattern only, and this one as a interacting spiral chaos. Now, if we move to the Ivy-Lev functional response, two-parametric bifurcation diagram will be equivalent to the bifurcation diagram that we obtained for Rosenwig-McArthur reaction kinetics, and stationary patterns are of similar kind, but there is a little bit difference. Whenever we have obtained this mixture of spot and stripe, so in case of Ivy-Lev functional response, the stripes are comparatively long if we compare with the mixture pattern, that means mixture of stripe and spot in the presence of Holling type 2 functional response. But this pattern is more or less same. But if you look at minutely that what is the range of distribution of this component, so there is a significant difference in the distribution. And one more interesting observation, as far as our effort was concerned, we tried a lot, but for any parameter value, we were unable to detect any spiral pattern, even interacting spiral chaos. But the type of chaotic pattern we observed here, that spatiotemporal chaos exists, but pattern is little bit different. It is not an interacting spiral chaos, as per we can see the structure of the patches. Rather, it is a wave of invasion. So chaotic wave of invasion that we have observed. And again, in this case, if we look at the corresponding distribution, that means distribution of spatial average with respect to time, now you can see there is a drastic change in the distribution of the spatial component with respect to the stable equilibrium or stable steady state of the corresponding temporal model. So you can see in this case, the spatiotemporal distribution is encircling the equilibrium point of the corresponding temporal model. Even for spatiotemporal chaos, this chaotic distribution of the solution trajectory is around the homogeneous steady state, and this is a significant difference if we compare the spatiotemporal pattern for the model with Holling type 2 functional response and model with Ivy-Lev functional response. Now, if we move to the third case, that is, if we consider the trigonometric functional response, that is tan hyperbolic functional response, then you can see there is a two new domain, that is R2 dot and R1 dot. These two domain arises due to the presence of this particular saddle node bifurcation threshold of limit cycle. So this K star corresponds to Hopf bifurcation threshold. It is subcritical, that we have to keep in mind. In earlier two figures, it was supercritical, but here it is subcritical. And this one is the saddle node bifurcation threshold of the two limit cycles observed for the temporal model. And most interestingly, what we observed here in literature, it was reported that spatiotemporal chaos you can observe for parameter values which lies on the right hand side of the Hopf bifurcation threshold. That means once your parameter value within the Hopf instability region, then only you can have some sort of spatiotemporal chaos. But here it is Hopf threshold. Even on the left of Hopf threshold, we can have some spatiotemporal chaos, and that is an interesting structural sensitivity for spatiotemporal pattern formation with Rosenwig-McArthur model in presence of self-diffusion as well as cross-diffusion. So if we choose parameter value from R1 dot, you can see this kind of pattern. So that means for parameter values on the left hand side of the Hopf bifurcation threshold, model with Holling type 2 functional response and Ivy functional response never produces any dynamic pattern. But for trigonometric functional response, on the left-hand side of the Hopf bifurcation threshold, we have this kind of pattern, and which you can see of this type. This is not chaotic, rather it is quasi-periodic with dense assemblage of the trajectory. It is actually quite rapid, and that is due to the fact that the basin of attraction of the coexistence steady state is very narrow, and that you can probably try to understand from this picture. So this unstable limit cycle is actually some sort of basin boundary for the homogeneous steady state, this one. So that is why in spatiotemporal context, the cycle rotates around this value quite rapidly, and that actually leads to this kind of dense assemblage of the trajectory around the homogeneous steady state. So this much we have done. Lot of different things we have to check. What is going to happen if we consider nonlinear death rate of predators, if we consider prey as well as predator dependence functional response. So many things are pending. I am not going into that part. And this is the paper where we have reported all these details in just 2024. And this paper I mentioned in my last talk also. I liked it very much because here we have shown that 1-1 correspondence between the dynamics observed for the model with dimensionless parameter as well as for model with dimension. So that is a 1-1 correspondence. And then one can try to understand that how this kind of pattern diagram can change with the change of functional response. That would be our future direction. This figure I just prepared out of my curiosity. And if anybody wants some explanation for this figure, I can give that explanation. But of course, personally, even I use this kind of diagram in couple of my papers, but it cannot capture the exact essence of the pattern formation, because for several parameter set, we can have more than one stationary solution. Those cannot be captured or those cannot be guessed from this particular figure. But this actually summarizes that what different type of patterns we can observe in different parametric domain. And of course, in this case, we have this as a Turing-Hopf domain. This is pure Turing domain. This is stable domain, and this is Hopf domain. Not for this model that I have shown. It is for a different model, because the previous model I have shown, in that case, Turing domain was above the Turing instability curve, and that curve looks like this one, not for this one. So here the fundamental difference is that we have actually chosen D into the first equation. That means dimensionless ratio of diffusivity present in the resources component, and in consumer component, it is exactly equal to 1. So that's why Turing bifurcation curve looks like this one, and Turing domain is below this particular curve. But other interesting question that of course one can explore, that how structural sensitivity affect other type of patterns like traveling wave, 3 different types, wave of invasion, as well as standing and moving pulses. And also another branch of open question remains, that how the spatiotemporal bifurcation structure and also spatiotemporal pattern formation for models with more than 2 components. So here I confine myself only with 2 components. That means activator, inhibitor, or prey and predator. But of course, one can consider prey, predator, super predator, or several other systems which have 3 or more components. So how this structural sensitivity can affect in those areas, those are very interesting areas of research. And this just came in my mind. So that is why I wrote it in this slide. So one can try to have a look at the idea that structural sensitivity in case of model with prey as well as predator dependent functional response, how it will be results in there. And also the taking care of the evolutionary aspect, that this functional response Fn is a linear combination of these functional forms, that is Holling type 2 and Ivy and tan hyperbolic, just to have an essence of the thing that functional response looks like some of them, but not exactly equal to any one of them. And one can try to find out some way out that how we can keep on changing these parameters with respect to time, such that their sum will be equal to 1 at every time point. And this is nothing but a convex combination of these three functions that actually constitute the indefinite functional response. Okay, so these are some references, and then this work mainly done with Kollan and Sergey that I presented today. And these are my other collaborators with whom so far I have worked a little bit on structural sensitivity of the spatiotemporal pattern. And thank you very much for your kind attention.
Yes, thank you, Maley, for this interesting presentation. All these very nice patterns. Always interesting to see them. We have some time for the discussion, so please, you can ask your questions from the audience. So I would like to start with slide 11, please.
Okay, slide 11. Okay.
Yes, you show here this diagram with different regions and with different instability conditions, Hopf and Turing. But in the next slide, you show already patterns. Please show the next slide. Yes, this one. Some of these patterns are indeed can appear near the stability boundary, but probably spiral patterns do not. So they don't appear as a result of probably as far as the set of small perturbations of this homogeneous in space stationary solution. So could you comment, please, how these patterns which we observe here are related to the diagram in the previous slide? So is it close to the stability boundary or it is far from the stability boundary?
Yeah, so if we just consider the spiral pattern we have obtained for k equal to 1.2, d21 equal to 1. And this interacting spiral chaos we observed for k equal to 4.5 and d21 remains same at 1. So now if we go back to the previous slide, so this is the Hopf bifurcation threshold. So k equal to 1.2 lies somewhere here corresponding to d21 equal to 1. And then k equal to 4 point something that is far away from the Hopf bifurcation threshold.
Yes. Okay. So, but spirals themselves, they do not appear as a result of bifurcation from the homogeneous steady state, or they do appear. I think that
they appear because that means Hopf instability with some inhomogeneity in the initial condition with a special type of heterogeneity in the initial condition as it was introduced by Sergey and Horst Malchu in 1999 in their paper which was published in Mathematics and Computers in Modeling. So that similar kind of specific type of initial condition I have used to capture this spiral pattern. And as per your question, that yes, the spiral pattern obtained within the Hopf instability region. So as far as my understanding is concerned, at least one instability is required for the generation of spiral pattern. So here that instability of temporal component, that means Hopf instability, is sufficient with particular type of initial condition that can lead to this type of spiral pattern, at least for this model.
Right. But let me just to ask an additional question to make sure that I understand correctly. Please return again to this previous slide. So there is this very vertical line, it's a Hopf stability boundary. So if you are very close to this stability boundary from the right, So will you obtain these small spirals with small amplitude?
If I recall correctly, we obtained spiral up to k equal to 1, but not very close to this value. But of course, in that case, one can raise the question that have you checked with all possible values of d21 close to this? Answer is no. So we have checked only for d21 equal to 1, d21 equal to 1.1, and d21 equal to 0.9. With this range of d21, and for values of k less than 1, we did not observe any spiral.
Yes, so please, if in future you can check, because I think it's an interesting question, quite general, because my understanding was, though I never worked myself on the spiral patterns, but my understanding was that spiral patterns do not appear from the homogeneous steady state, but rather appear as a kind of global bifurcation. But I may be wrong, or it can be different for different models. So it would be interesting to know for this particular model, do they really appear as an instability of the homogeneous solution and close to this homogeneous solution, or they appear as a global bifurcation far from the homogeneous solution?
Yeah, means the partial answer to your question is that we did not check that whether it results in through any global bifurcation or not. But what we observed that this spiral pattern appears due to small heterogeneous perturbation around the homogeneous steady state.
Yes,
that
but right, but
sure.
Yes, but the amplitude of the spirals, can you obtain the spirals with very small amplitudes?
That I have to check. That I have to check. Yes,
right.
That I have
because again, back to my question. So if it is a bifurcation from this homogeneous steady state, then for the parameter close to the stability boundary, you will have this spatial solution spirals very close to this homogeneous steady state, meaning that the amplitude will be very small.
Yeah,
so this is my question, in fact.
Yeah, a long back, we worked on a problem with Noina. That paper was published in International Journal of Bifurcation and Chaos, and there we have provided some analytical expression involving the parameters involved with the model. If those conditions are satisfied, then spiral exists. So that technique can be applied here just to find out such conditions, and which will give us the idea that is how far we have to be from this Hopf bifurcation threshold in order to have some sort of spiral structure. But the technique I followed from one paper that was published in Physical Review E by Devshankar Rai, entire part is not convincing to me. And whatever other result, those are available in the literature, mainly by J.D. Murray. They worked on the lambda omega system. And for this type of model, if we convert it to lambda omega system, so that validity of lambda omega system is very narrow domain near the Hopf bifurcation. If we move away from the Hopf bifurcation, even that lambda omega approximation is not correct. So I'm a bit confused that with that technique we can work, or even I can discuss with you afterwards that what kind of different global bifurcation I need to check for the onset of this kind of spiral pattern.
All right. Another question which I have, looking at this next slide, is different patterns, but this question also concerns, in fact, all these results about the about the role of this cross diffusion terms D21. So which of these patterns you can obtain with this coefficient equal to 0, and which patterns can be observed only for this coefficient different from 0? Could you summarize this?
Yes. With D21 equal to 0, we have obtained only this interacting spiral chaos among the patterns shown in this particular slide. Of course, with D21 equal to 0, we can have another invasive patchy pattern, but we were unable to detect such kind of invasive patchy pattern with D21 not equal to 0, because according to my understanding, as we are considering cross diffusion, so cross diffusion means predator is already present there and it follows the prey density. And if we introduce very small amount of predator in order to check whether there is successful invasion or not, so that most of the time leads to the situation that predator goes to extinction and prey moves to carrying capacity. So precise answer to your question is that among these 5 patterns, only interacting spiral chaos can be observed for the model with D21 equal to 0.
So, for example, this left image with one spiral you don't observe, right?
No, we don't observe any one spiral.
Yes, yes, this is interesting. All right, so then maybe if you can show slide 13, please. In fact, it's the next, yes, the next slide. Yes, I was also interested by this, by these results, that these oscillations or these patterns appear far from the homogeneous steady state. So how would you explain it from the point of view of bifurcation of these patterns? So in other words, how these patterns emerge? Do they emerge from this red dot, from the homogeneous steady state, and go away from it as you change parameters, or they emerge directly far from this homogeneous steady state?
Yes, actually it emerges far from homogeneous steady state, because if we just consider the complete time evolution of the solution trajectories, so if we plot that, because here we have plotted by discarding a long range of initial transients. So if we want to plot the entire time evolution of the solution trajectory starting from the initial point, so it will start moving around these for a longer time, then it remains there for certain time, then it moves in different direction. But once the long transients are gone, then ultimately they settle down in this kind of structure. So what is my belief is that Hop bifurcation, that is periodic solution that we observe for the temporal model, those are in 1:1 correspondence for the spatiotemporal model if we consider D1 and D2 both pretty close to 0. But here, as we have considered D1 equal to 1 and D2 is greater than 1, so this spatiotemporal model is already far away from the temporal dynamics that we observe in absence of diffusion. And those spatial diffusion coefficients drives the system towards a different regime. And sometimes we have interpreted, depending upon the different reaction kinetics, that spatiotemporal heterogeneity, that means heterogeneous of distribution of the species, can enhance their coexistence level, or sometimes it reduces their coexistence level. As you can see in this case, the concentration of prey population increases compared to the temporal equilibrium state, but predator component has decreased. But in this case, both prey and predator components, they are increased compared to the temporal part.
All right. But I suppose that it depends also on parameters, right? If you change your parameters approaching to the stability boundary, so probably this attractor will move to the homogeneous state.
Definitely. And if we want to understand that bifurcation structure, frankly speaking, as of now, I don't have any idea apart from that some kind of beef tool algorithm. But I don't like beef tool algorithm, because beef tool algorithm is just considering the lattice version of the continuous time model. So they are approximating continuous time model with respect to discrete space. But if you consider that discrete space length is very small, so then there is, as far as my knowledge goes, there is no appropriate way or unique way to construct the bifurcation diagram, or in order to find out what is the route to chaos for spatiotemporal model.
All right, then also slide 20, please. You showed a nice picture and you give some comments about it. Yes. but still it's not completely clear for me. What it shows, in fact, it's kind of patterns I hear, or what is it?
Yeah, so here what we did, we have chosen a large domain, 500 cross 500. We have considered one model. Then at each lattice point, we have different values of one temporal parameter. Just for example, in the previous bifurcation diagram, on the horizontal line, we have k, and on the vertical line, we have d21. So suppose in this range, k varies from say 0.8 to 2.9, and d21 varies from say 0.2 to say 20. So these entire space discretized over a 500 cross 500 lattice. So each of the lattice point, they consist of different values of k and d21 corresponding to this axis level. And then the model is simulated with different values of k and d21 at different lattice point, and then we have observed that okay, any kind of pattern can be observed or not. So if you look at the pure Turing domain here, so it gives us homogeneous steady state, but practically, as I have mentioned, that it is not convincing, and or also it is not depicting the exact picture due to continuous variation in the temporal coefficient as well as in diffusion coefficient. It gives us a vague idea that in this region you cannot have any pattern, but actually there is pattern that is not reflected here. But interestingly, what is mostly observed, or what is most interesting part, is that in this entire range, we can say that okay, here we have this spatiotemporal chaos, and even we have a close look at this diagram. So in this part, patches or some branch of the spiral is a little bit thick, but here we have very thin arms of the spirals. And similarly, what we can say, over this entire range, we have spatiotemporal chaos, and in this range, we can have this stationary distribution. But this figure fails to give us clear-cut idea that how many different branches of stationary solutions can exist for this range of parameters. It is just some sort of heuristic approach just to understand for which combination of the parameters we can see what type of different patterns. And sorry, I can't recall exactly which reaction kinetics we used here, but it was interesting to show even within the Turing-Hoff domain, you can have hotspot pattern for some parameter values here, as well as cold spot here. And this cold spot actually continues to this Turing domain, but this heuristic approach of drawing the figure helps to capture heterogeneous distribution at this range.
All right, thank you very much for this explanation. And other questions from the audience? I don't see them. So thank you again for this very interesting presentation. It was really nice to learn more about all these spatial patterns, all this nice dynamics. So thank you again, and we finish our today's seminar. So
okay,
thanks to everybody, to all our listeners. Goodbye.
Yeah.